All right, so we're going to start vector addition today. The vector addition that we will start with is actually going to be familiar to you because you've done it already. Okay, you added collinear vectors in Science 10. Collinear vectors are vectors that share a line. That is, they have a forward, backward, positive, negative, right, left kind of relationship. They are the opposite of each other, which basically means all you ever had to do was add or subtract numbers to add vectors in Science 10. Okay, you might have had like a garbage truck travels 2 kilometers north, then turns around and travels 600 meters south. What's its average velocity? All you had to remember was that south is the opposite of north. Okay, pretty easy stuff. But we're going to go over it again because we want to establish how do we diagram this? How do we represent vectors visually so that we can start analyzing them? Okay, the whole point of vectors in Physics 20 is their analysis. Yes, there are going to be problems to solve, solutions to come up with, but we are very concerned with the analysis of vector problems in Physics 20. Okay, now that means that in Physics 20, we may do vector analysis differently than you did vectors in Math 10. Okay, sometimes teachers will teach vectors from the sine law, cosine law standpoint in Math 10. Okay, that's not how we do them in Physics 20. Okay, I'm not saying that you can't use sine law or cosine law to solve vector problems. You can, but what we find is that when you use sine law or cosine law, first off, a lot of people don't do it right. Okay, they don't understand it fully enough to correctly apply it. And secondly, that it does not lead to an understanding of the vectors. It doesn't allow you to analyze them. It just allows you to solve the problem and get an answer. Okay, we're concerned with, do you understand what's happening in this vector situation? Can you analyze what's going on from a directional standpoint? Sine law and cosine law do not allow you to do that. Okay, they just allow you to come up with an answer. Okay, and we're more concerned with the method. Okay, so we're going to look at vectors, at least when we get to the ones that involve angles. Okay, we're going to look at that from a sine, cos, tan, simple trigonometric ratio, so SOHCAHTOA. Okay, we'll be looking at it from that perspective instead, which can be a little bit more time consuming in terms of solving the problems than sine law or cosine law. Especially if you're good at sine law or cosine law, you can solve these problems pretty fast. Our method takes a little longer, but because it breaks the vectors down more, okay, you get a better understanding of what's happened, and that's important for not only Physics 20, but it's crucial to be able to analyze conservation of momentum problems in Physics 30. So that's a skill you have to develop. Okay, everybody with me there? Because it always comes up, Mr. Gooder, can you sign this with sine law? Do whatever you want with sine law, but okay, we need to be able to analyze the vector stuff here. All right, so first off, we're going to look at collinear vectors. Collinear vectors share a line. They're the vectors you're already familiar with. Okay, we're going to look at how we add all types of vectors and how we draw all types of vectors. Okay, vectors are always added by placing them tail to head. Essentially, we draw a picture that diagrams out a story. Okay, this person went this way for this far, then they went this way for this far, and we draw one happening right after the other. We kind of, draw it chronologically. Okay, we need to understand that vector quantities obviously have magnitude and direction. We've already gone over that 100 times. Okay, don't forget they have magnitude and direction. Okay, and understand that all vector quantities are added the same way. Okay, it doesn't matter whether I'm dealing with displacement, velocity, acceleration, force. All vector quantities are added exactly the same way. All that changes is at the end, the units you put on. Okay, so if I had two forces together, the diagram would look the same as if I had two displacement vectors put together. All that would happen at the end is instead of meters, I would have newtons, okay, as my units. But from a vector standpoint, the math is identical regardless of what vector quantity you are adding. Okay. All right, questions so far? Okay. So a vector quantity deals with both magnitude and direction. So when we draw a vector, we have to represent both parts of that. We have to represent its magnitude and we have to represent its direction. So a convenient way to represent that is by drawing an arrow. So all vector quantities, regardless of whether they're position, acceleration, force, okay, velocity, they're all going to be drawn as an arrow, right? We will represent the magnitude by the length of the arrow. And obviously the direction will be the direction the arrow points. Right? So if I'm given a vector, okay, like, well, let's just say, I'll get one here. Okay, say I've got that vector and I want to draw it. 20.0 meters at 10 degrees south of west. All right, so just in case we're not familiar with a compass. Okay, which way is southwest? This way. All right, now I've written 10 degrees south of west. Where's that measured from? From west, right? It's measured from here. 10 degrees south of west is not the same as 10 degrees southwest. Okay, 10 degrees southwest is not a good way to write something because that's two different directions. That could be this way, which would be 10 degrees south of west, or it could be this way, which would be 10 degrees west of south. They don't point the same way. Okay, they're in the same sector, the southwest sector, but they're not the same direction. So we always write a vector as it's south of west or west of north or whatever. Okay, it's going to be one vector measured from the other. Right? So if I'm drawing this as 20 meters at 10 degrees south of west, I draw a compass and I kind of go, all right, so it's going to look something like that. And then I do this. Here's my west reference line. I'm going to go 10 degrees south of that. That's probably more than 10 degrees, but all right, I've just drawn that vector. That is a vector that is 20 meters long, 20.0 meters long, 10 degrees south of west. Okay. Now, by comparison, if they wanted me to draw one that was 10.0 meters long at 10 degrees south of west, how would it look different? It would be shorter. How much shorter? Half, right. Now, I am not saying that when we draw vectors, you have to figure out a scale, pull out a ruler, and measure everything. That's ridiculous. It takes way too long to do that, okay? Just keep scale in mind when you are drawing, okay? A 10-meter vector and a 50-meter vector should be nowhere near the same length when you draw them, okay? Especially if they're on the same diagram, okay? Because that'll get really messy really fast, all right? So the general conventions here that we have to get for drawing vectors, not even for adding them yet, just for drawing them, is that they are an arrow. The length of the arrow represents the magnitude. The arrow points in the direction given. All right, everybody okay with that? Okay, now with this south of west thing, okay, you do have to be fairly familiar with a compass because we're going to use compass directions a lot, okay? Whatever direction is listed second, so south of west, is the one you draw from. So I drew a reference line that was west, and then I went 10 degrees south of that to figure out where my arrow was going to go. Okay, that's always the way we do it. So you can do it that way. Okay, some people, you know, if they're more like bodily kinesthetic, they like to kind of go, okay, this is west, and then they go like this, and that's 10 degrees. Whatever works for you. Okay, whatever is going to get you that picture. Okay, that's what you've got to do. All right. People always try and hide when they're doing the hand thing. I see them on their final exam. They're like, just do it. It's not a big deal. Nobody's going to laugh at you. Okay. All right. So everyone clear on those two conventions for drawing? Okay. And then this is the other part. The length of the arrow is proportional to the magnitude of the vector. Again, you don't have to come up with a scale and stick by that scale. Just keep scale in mind when you're drawing. Now, lots of times it's going to be necessary to add two vectors together because one thing happens and then something else happens after that. All right, so what we have to do is then draw the vectors as they happen. So with this one here, okay, we have a situation where, okay, a car moves 275 meters due east, okay, along a straight line, and then moves 125 meters due east. All right, so both of these vectors point east, all right, and they happen one after the other. So I draw the first one, okay, that's 275 meters. pointing due east. Okay, then they said right after that, it goes another 125 meters east. So I put that onto the head of the first one. Okay, and I've somewhat reflected scale here. My 275 meter long vector is considerably longer than my 125 meter long vector. Okay, as long as that's approximate and kept in mind, you won't have any trouble.
It says due of a direction, that means directly.
Directly along it, yeah. Okay. All right, so I draw vectors always tail to head. Okay, that was what we underlined on the very first slide. This is what tail to head looks like. Okay, we draw them one after the other because that helps us to show this one happened and then that one happened. All right, I do not want to draw it like this. First I went 275 meters and then I went 125 meters. That diagram says I did both at the same time, split myself in half at this point, and part of me went there. Okay? All right? Or even worse, I have people do this when the directions aren't the same. Okay? They'll say, all right, I had, first the car went 200 meters at 30 degrees north of east, and then it went 10 meters due south. So you're like Don Quixote who got on his horse and rode off in all directions. Okay? You can't do that. That says you physically split in half and did two different things at exactly the same time. Okay? What this diagram should look like is this. Okay? Well, that should be 100 meters, whatever. Okay? We've got first that vector, then this vector. Okay? Because in reality, now, if I go from here to here, will that line represent my total displacement? Yeah, because that's where I ended up. I didn't end up in two different places. Okay, but if I draw it the way I did it first, it says I ended up in two different places. That's not possible. Right? So we always draw it chronologically. First this happened, then this happened. And then if there was a third one, okay, let's say after that it went 50 meters due east, okay, then I'd put that on there because it happened after that one. Okay, and I just keep going until I get to the end. Okay, everybody all right with that? Okay. All right, so obviously if I'm adding collinear vectors, it's really easy mathematically because they're either going to be added together or they're going to be subtracted because they can only be positive or negative. Okay. All right, so everyone's good with the tail to head thing, drawing it chronologically. Okay. All right, so when we do this, this is just the math of it, okay? We're saying it's done tail to head, okay? Always, all vector addition is done in that manner. Again, doesn't matter whether it's force, acceleration, velocity, displacement, any vector quantity is added this way. Okay, now we're going to look at something you didn't do in Science 10. Now we're going to look at perpendicular vectors. Okay? Stepping stone to vectors with random angles. Okay, right now these vectors are perpendicular, so one is east, the other is north. Okay, they're right angles to each other. So in this question here, it says that I have a car that first traveled 275 meters due east, and then it turned and went 125 meters due north. Okay, so have I still drawn that diagram tail to head and chronologically? Yes, okay, because I said, here's my starting point. I went 275 meters due east, okay, and then I went 125 meters due north. I drew this one, okay, onto the head of the first, tail to head. All right. So I ended up here. So my total distance would be 275 plus 125, okay, so it would be 400, but my displacement is which line? The red one, okay? My displacement would be this line here. All right, so how am I going to calculate my displacement? Sorry? Okay. Who's the guy who figured that out? What was his name? How to calculate the hypotenuse? Okay. Okay. He's the Greek geek, Pythagoras. Okay, Pythagoras is the Greek geek because he spent his whole life studying triangles. Life wasted. Yeah. Okay. But anyway, it's important. He discovered something important. But okay. So we've got Pythagorean theorem here. That's where we take a squared plus b squared equals c squared. All right. That's how I would calculate the magnitude of my displacement. That'll only tell me how long the hypotenuse of this triangle is. I'm trying to calculate displacement, which is a vector quantity. So while that's good, I have the magnitude, I also need to find the direction. All right. That means I want to find theta. Since I know two sides of that triangle, can I find it? All right, which two sides of the triangle do I know? I know so this is where my angle is. This side is adjacent to my angle, and this side is opposite. All right, so I know the opposite side and the adjacent side. And realistically, at this point, I probably would have already done Pythagorean theorem, and I would know the hypotenuse. Could I use any of the trig functions I wanted at this point? I could. Here's my caution on that. I would use these two numbers because the question gave them to me, just in case I messed up on a calculation and then I'm using a number that's wrong. Okay, that's going to increase the mistakes I make within the question. So as much as possible, I try to use ones I didn't have to calculate myself. All right, so I have the opposite side and the adjacent side. Which trig function is that? Okay, it's tan. Okay, I'm going to use the opposite side and the adjacent side to calculate this angle. All right, so remember, the tan of theta equals the opposite side divided by the adjacent side. Okay, I'm trying to find theta, so that manipulates out like this. Tan to the minus 1 of the opposite side divided by the adjacent side equals theta. Okay, so this is where I was saying you're going to do these trigonometric ratios that hopefully you learned like back in junior high, but were cemented in your mind in Math 10. Okay, so for this one here, that's going to be 10 to the minus 1 of 125, my adjacent or my opposite side, okay, which was 125, divided by my adjacent side, 275. Okay, what mode does your calculator need to be in for this? Degree, double check. You'll get really wonky answers if it's not. Okay, so we're going to have second tan of 125 divided by 275. And I'm in radian mode. See, that's the wonky answer. Okay, mode. Yep, I'm in radian mode. Degree, better. All right, so I'm getting 24.4 degrees here, okay, as my answer. Okay, which direction is that? North of east. Here's how I know it's north of east and not east of north. Okay, that angle arc that I drew touches this direction, which is east. So this angle is measured from east. It's moving north of east. Okay, everybody with me there? That's how I figure out which directions to put on there. This is 24.4 degrees north of east. All right, so I've got that, north of east. I still haven't got the magnitude. I said I was going to do a Pythagorean theorem calculation, and then I never got around to it. Okay, so the magnitude of the displacement is going to be 275 squared plus 125 squared. All right, so we're looking at 302 meters. Okay, so my final full answer would be 302 meters at 24.4 degrees north of east. Okay, so the individual pieces of a question like that are things you have done hundreds of times already, okay? Doing a tan calculation, doing a Pythagorean theorem calculation, okay? You guys have been doing that kind of geometry for years already, okay? It's just this is a different context or a different application of that concept. Okay, so quick review here. I represent a vector by drawing an arrow. Magnitude of the arrow, length of the arrow represents the magnitude. Angle is represented by or direction is represented by which way I point the arrow. Okay, I always add, if I have more than two vectors or two or more vectors, I always draw them tail to head. So I draw the first one, then I draw the second one, then the third one, the fourth one, however many they're going to be, but I draw them chronologically, connecting them tail to head. Okay, and then from there, okay, if I just have two vectors and they're perpendicular, then I can use Pythagorean theorem to get the hypotenuse, which would be my total displacement in this case. Okay, if it was two velocity vectors, it would be my average velocity. If it was two acceleration vectors, it would be my average acceleration. If it was two forces, it would be my net force. Okay, I would add them together in the same way regardless. And then I would use trig to find the angle or the direction of my overall vector, okay, which we typically call our resultant. Okay, so that last arrow, that red arrow on here, okay, this did represent displacement in this case, but in general, we call that line that connects the beginning to the end of the vectors, we call that the resultant. Okay, because it can obviously represent different things depending on what vectors I added together. Okay, questions on that? Right. That's the fundamentals of vector addition. Okay, now I'm not going to say that's where it ends. Okay, we haven't even gotten into the danger zone yet. Okay, but that's at least the fundamentals of it. Okay. All right, so this is just the math of what we did there a second ago. Okay, let's have you guys try this one. It's easy, super easy. Collinear vectors, super easy. Okay, give you a minute on that one. Okay, so mathematically not a difficult question. So in like South Boredom, USA, the most boring town in the world, they do this race. I don't know, seems like a pretty boring place to live where this is like your winter highlights or something. Okay, so you have a snowshoe race. You move forward 10 meters and untie a bunch of knots. Yay, okay, so we'll draw the 10 meters, okay? Then they move forward 5 meters and solve a puzzle. Okay, am I representing the magnitudes okay? Right, that line's about half as long as the first one. Then they go forward 25 meters to the finish line. And that's about 2.5 times as long as the first one, something like that. Okay, again, I don't need to actually measure it. As long as my scale is approximate, I'm good. All right, so what's my total displacement here? It says determine the resultant vector, which is a displacement vector in this case, graphically. 10 plus 5 is 15, plus 25 is 40 meters forward. Okay. Obviously, you probably wouldn't need to draw a vector diagram for something that's simple. All right, but it's just the purpose of kind of running through the exercise of it. Okay. Okay, I want you guys to try try question 7. I would never give you one like this, but this is a bit of a math, more of a math one than a vector one, but there's a vector component to it for sure. Okay, give you a few minutes to work on that one. All right, so if we're looking at 7, the first thing we have to do with number 7 is we have to figure out what their, well, they actually tell us what the overall displacement is. The overall displacement over this whole trip is only 50 kilometers. They went 500 north, but they end up that when they come back, they're still 50 meters north of where they started, which means that trip back is how long? 450 kilometers. Okay, so that's the first thing we have to get, is that those 3 segments add up to 450, not 500. Okay, so that's the first thing. Now, here's the thing. They don't tell me what the first length is. Okay, all they tell me is that this 450 meters is what the three things add up to. But they do say that each one sequentially is 50 meters longer than the one before, 50 kilometers, sorry, longer than the one before. So here's what I'm going to say. I don't know how long the first one was. So it's just going to be n. The next one is 50 kilometers longer than that one. So how would I write that, not knowing what the first one is? N plus 50. All right. And then the next one is n plus 100. Okay. Can I isolate n? Yes, I can. I'm going to subtract 150 over from this side and bring it back over here. So I'm just left with n plus n plus n. So what I'll be left with is 300 equals 3n. How long is n? 100. The first length is 100 meters long, or 100 kilometers, sorry, long. Okay. Everybody all right with that one? That's a math trick. It's not really a physics trick. Okay. All right. Okay, I want you guys to try this one. This one you're going to have to draw tail to head. Okay, it's going to be perpendicular, so you have to do a little bit of trigonometry. Okay, but it's not that hard. So I want you guys to try that one. Calvin, question? How did I draw the last one? Okay, basically on that last one I did this. I said I had this, which was n, and then I went I drew three vectors, none of which I actually knew the length of. Well, I mean, I could have, but I didn't need it, right? I guess is why I didn't draw it. I only needed to know about the 450 I did travel back. Right. Okay, so give that one a try there, guys. See how you do on that. Okay, so we want to draw our vectors tail to head. All right, so the first thing is that she walks 0.8 kilometers south. So I'm going to say this is her starting point. She's going to walk 0.8 kilometers south. Then she goes 1.2 kilometers east. All right, again, I'm reflecting scale here. That's about, 1.5 times bigger than the 0.8, okay? And it's pointed due east. Then she goes 0.3 kilometers north after that, okay? Which is a little less than half as long as my 0.8. All right, so I followed scale. I've drawn them tail to head. They all point the right direction according to the question. So where would I draw a line that represents her total displacement?
From the her initial point, the arrow goes.
Exactly. Okay, from start to finish. That's always what displacement measures. All right, so there's the vector that represents her total displacement. Now, over the course of the entire trip, she goes east and south. Okay, she ends up east and south of where she started. Everybody all right with that? Can I figure out this and this? Okay, the x is pretty easy. How big is x? 1.2 kilometers, right? So we're making a rectangle here. All right, so x equals 1.2 kilometers east, okay? And y equals 0.5 kilometers south. All right. So the question wants me to calculate her overall displacement, which would be the length of this line with that direction. Can I find those two things? Okay, this is what essentially all multi-vector problems break down to, is finding out the horizontal and vertical components of your overall vector, okay, of your result, and finding out how much to the side and how much up or down it goes in total. All right, so now that I have that, I can calculate the magnitude of D using Pythagorean theorem. I'm going to find, then I'll find the angle using tan. Yeah. Okay, so I've got, in this case, the magnitude of D will be 1.2 squared plus 0.5 squared. Okay, and that'll tell me how big that is. All right, so we're getting 1.3 kilometers. All right, so it's her total displacement is 1.3 kilometers from where she started. But now I also need to know what direction that's in. Okay, so I'm going to say that theta, okay, is going to be opposite over adjacent. So that'll be tan to the minus 1 of 0.5 divided by 1.2. All right, so I'm getting an angle here of 22.62 degrees. And which direction is that? South of east, right? She went south and east. This line here is east, and I went south of it. So it's going to be south of east. All right, so now I just got to check out significant figures here. Okay, looks like I've got 2. Okay, these two only have 2. So we'll have 1.3 kilometers at 23 degrees south of east. Is there another direction I could give that would also be correct? Could I say how many degrees east of south? All right, what angle would that be? Thank you. 67.4. 90 minus 23 is the other angle, right? Okay, so the other angle that I could write would be, okay, I could write 1.3 kilometers at 67 degrees east of south. And that could happen because not everybody would draw the triangle this way. Some people would draw it like this. So when they calculate this angle, it's going to be this side is the opposite and this side's adjacent. It's the same direction, okay? It's just from a different reference point. Okay, everybody good with that one? No.
When you do the 1.2 squared plus I squared,
yes. Yes, because it's c squared equals a squared plus b squared. So I have to square root to get c. Yeah. All right. Any other questions on that one? All right. That one we can skip. And that one we can skip. And we've done that one already. Okay. Okay, so the purpose of this question is to illustrate a couple of things. First off, that what we were doing before, all the questions we were doing had to do with finding an overall displacement. This is going to be finding an overall velocity. Doesn't change what we do. We're still going to draw these as arrows. We're still going to point those arrows in the directions they tell us, and we're still going to draw them tail to head. Okay, so the way we draw this looks something like this. Here's my river. Okay, it is 200 meters wide. Right, that's a displacement vector. Okay, now the two speeds we were given were a rowing speed, and that was 2.5 meters per second, right? Okay, and then there was a current speed of 1.2. Okay, if I'm rowing across the river, are both of those velocities happening at the same time? Yes, but they're still going to add up to me doing this overall. Okay, if I had like a drone and I popped it up in the air above the river, above me where I'm rowing, what it's going to see is me moving diagonally across the river. Okay, it's not going to see me going across and then down. It's going to see the result of both of those things happening at the same time. But we still draw it like one happened and then the other. Okay, because that's what the final product is going to be. Okay, so if I'm trying to find the resultant velocity of the boat, that's still the hypotenuse of this triangle. Right? And I would calculate it in the same way we did all the other ones. Okay? The resultant velocity of the boat will be the magnitude of this line, and the direction will be this angle, which will be east of north. Okay, so to calculate that overall resultant velocity, okay, I would just take the Greek geek here. So 1.2 squared plus 2.5 squared. Whoop, not 25, 2.5 squared. Okay, so the overall velocity or resultant velocity is going to be 2.8 meters per second. That's the magnitude. Okay. To find this direction, I'm going to use tan, opposite over adjacent. So that'll be second tan of 1.2 divided by 2.5. All right, so I'm getting that angle is going to be 26 degrees. So I would just write on here, at 26 degrees east of north. Right? That's my resultant velocity. How do I get B?
Calculate how long it would take to do that trip.
Yeah. Okay. I can calculate how long it's going to take to get across the river. I can do that because I know how fast I'm going across the river, and I know how far it is across the river. Okay. I know it's 200 meters across the river. How fast am I going across the river? 2.5 meters per second. Okay. Why do I not use this that I just calculated? Is this across the river? It's not, okay? It's somewhat across and somewhat down. I can only use this vector with this vector. They point the same direction. I can't use a vector that doesn't point in the same direction, okay? So I have V, 2.5, and D, 200 meters. So I can calculate the time to get across, okay? The time to get across the river will be 200 divided by 2.5. T equals D over V. All right, so I calculate that, 200 divided by 2.5. All right, it's going to take me 80 seconds to get across the river. The whole time I'm rowing across, what am I also doing? Being pushed downstream. How fast am I being pushed downstream? 1.2 meters per second. So if I take the 80 seconds and multiply it by the speed I'm moving downstream at, I find out that I will end up 96 meters downstream. Okay, east. Yeah, you could say, yeah, we would say east because I gave east in the question, but if it didn't give east, you'd say downstream. Yeah. Did you find out how far that line would be? You
No,
went,
I did 2.5 meters north for every 1.2 meters east.
You essentially did what we did. That you found the
Okay.
ratio, but yeah, it's different. I mean, it'll work.